So, hi everyone. In this video, I am going to discuss about demand paging. So, it is a memory management technique that allows program to access memory only when it is needed. So, in other words, we have process and then that process is being broken down into pages. And a page will only be brought into the memory when it is needed. So these are some of the advantages. So there will be less I/O needed, and there will also be less memory needed since those pages that are not really used by the CPU will not take space into the main memory. Okay, and there will be also a faster response and more users or more concurrent na programs running since there will be more available na holes into the main memory. Okay, since we swap out those um, pages that we don't need. Okay, so we have what we call a lazy swapper, wherein we never swap a page into a memory unless the page will be needed. Okay, so we can see here an illustration, assuming we have the main memory. And then we also have the secondary memory. So initially, let's say the main memory is, there are still a lot of free holes into the main memory. And initially, our processes will be stored in the secondary memory. So you can see here process 1 and process 2. So process 1 has 7 pages and process 2 has 4 pages. Okay, so in case that we need these pages, let's say A, B, C, and D from process 1 and E, F, H, and I from process 2, we swap it in from the secondary memory to the main memory. But let's say that these pages are no longer required. Initially, the C, the H, and then the I. So we no longer need these pages. So we swap it out of the main memory and put it back into the secondary memory. Okay, so assuming that the CPU needs H. So initially H was here, right? But we already swapped it out of the main memory. But in this case, H is no longer present in the main memory. So since CPU is requesting a page that is no longer or that is not loaded in the main memory, a page fault occurs. Okay. So we have here an illustration again. So how does it actually CPU reference a certain page? So it is through the logical address, the page, and the offset. So let's say we need P2. We need P2, process 2, and then as you can see here, the page 2. So that means that we are going to need this page 2. But then we can see that the bit is invalid. So going back here. Okay, so we have the secondary memory and the main memory, right? And for each of the process, we have a page table. And the page table maps the logical address with a physical address. So as you can see here, let's say in this first row, we are mapping frame 0. I mean frame 1 with page 0. And then the second row maps the page 1 with frame 2 and so on and so forth. But you can see here another third na column, which is V or I. So what does it represent? So V and I represent the valid or invalid na bit. So this is just a mechanism or a way for us to check if a certain page is in the main memory or not. So for example, this one, pages A and then B, so 0 and 1 rather, are loaded into the main memory. So we set its bit as valid or V. Okay, and for process 1 also, page 3 is loaded in the main memory. So it is also set as valid na bit. But the rest are set as invalid. Okay, and for page 2 on the other hand, we can see that this page 0 and 1, which is E and F, are loaded into the main memory. So that's why they are also set as valid. So otherwise, I. Okay, so malalaman natin yung purpose niyan later. So assuming that the CPU needs this page 2 from process 2. Okay, and then when we check the page table, and we can see that page 2 has an invalid na bit. So that means that the page 2 is not loaded into the main memory. So since the CPU is requesting a certain page that is not loaded in the main memory, we have what we call a page fault. So what we do here is we transfer the control to the OS. So we set an exception, transfer the control to the OS or the operating system. And what the operating system does is to request that desired page, which is page 2 of process 2 from the secondary memory. Okay, so we know that it is page 2 and it contains the word G. And then once we have found it, we are going to load this desired na page into the main memory. So we are just going to look for available na holes in the main memory. So assuming that we load it in the frame 3, G in the frame 3, okay? So after that, we are going to update the page table of process 2. So since the page 2, which contains this G, is loaded in frame 3, so we update its frame as well. And we also change its bit into V or valid, meaning it's already loaded in the memory. Okay, so after that, we are going to restart the instruction. Since CPU needs this page 2 again, and as you can see, it's already valid. So CPU can now access this page. Now, page faults are expensive though. So what are page faults again? Page faults happen when the CPU is requesting for a certain page that is not loaded in the main memory. So the process spends most of the time paging in and out instead of executing code. So if we go back here in our process, so if we see that there is a page fault, what the OS does is to request again the request from the secondary memory, page in, and then update the page table. So all of this process take some time. All right. So if there are a lot of page faults that are happening, so that would also cost us less efficient na time or process.